So aggravating. All right, continuing again here. All right, so state vectors, these form a complete orthonormal basis for the associated Hilbert space to the problem. All right. It says, finally, in classical mechanics, both the state and the observable depend on time t, but no such characterization holds true for the state and observables in quantum theory. It follows from postulates 1 and 2 that the state or wave function psi of xt can change with time t, but the observable operator A, along with its eigenbasis and its real eigenvalues, are all independent of time. So we express the wave function psi of x comma t, all right, as follows. The sum n equals 1 to infinity of psi n, bracket with capital psi here, bold psi, with psi n of x. Now, obviously, what's that?
Sorry, that's it.
Oh, okay, cool. So obviously, if psi n of x is not a function of time, it must be the bracket here where the time dependence is coming into play, right? Like these have to be somehow time dependent, right? And in particular, this is calculated. They're time dependent scalars of the following form. So, you know, I wouldn't try to think too deeply about this. I feel like in some sense parts of these things I'm writing really just setting down notation. Not sure I'm really doing anything except for giving you what this notation means, you know.
Doesn't introduce the time factors.
Right. That's coming up. That's coming up. Like that for n equals to 1, 2, 3, and so forth. All right. All right. Such an expansion of the wave function in terms of the eigenbasis for the observable A hat plays a fundamental role in the development of quantum mechanics. However, the fact that A hat, psi n of x, and lambda n are all independent of time does not necessarily mean that the measured values of the observable A hat will be constant in time. At any rate, it remains to be specified how the result of a particular measurement depends on the state of the system at the time of measurement. That's what he's about to do, okay? It's then necessary to establish some sort of logical connection between the physical observables in classical mechanics and in quantum mechanics. Now, that's an interesting perspective. It's certainly not one that's shared by all practicing physicists. You will find physicists, you know, honest to goodness theoretical physicists who will tell you that quantum mechanics is basic. See, he's taking the perspective that classical mechanics is basic, and it's something you know, there's something you do to classical mechanics to produce quantum mechanics. Well, I mean, that's a useful viewpoint in as much as you understand classical mechanics, right? But from a physicist's perspective, they might say quantum mechanics is fundamental, right? So from that perspective, some aspect of what we're saying is in some sense meaningless, which is why it's not a problem that there exist things in quantum mechanics which have no classical analog. Like not every thing that you study in quantum mechanics has a classical analog. But many things do, and here's a nice list. And certainly I think that, you know, talking about this correspondence and so forth is, at minimum, it's important to the, you know, the history of quantum mechanics, if nothing else. So you've got observables. All right. And here's your classical. And here's your quantum. All right. And we've already seen this. There's position, momentum, well, linear momentum to be more specific, and then linear momentum with a vector, kinetic energy, Hamiltonian, angular momentum, and then angular momentum in the vector sense. So, of course, typically, classically, we either use x or we use r vector, right? And over here, you use x hat and, you know, I don't know. I guess you could put vector hat. I think in practice, they're like boldface with a hat over them in books, but I'm not good at boldface on the board, so I'm kind of stuck. All right, whatever. All right, linear momentum, you got px or mx dot, right? And over here, you've got p hat sub x, which is minus I h bar partial x. Still no explanation for why that is, by the way, right? And then, of course, you also have momentum as a vector, which is, you know, px, py, pz. And then over here, you can talk about a vector of operators. P hat minus I h bar nabla. This is a vector of operators in the sense of minus I h bar partial x comma partial y partial z. That vector of operators that physics equations have a habit of using. Let me not try to define that carefully here. It does have a meaning. It's not, you know, anything too. It's more or less a short.
Strange that when we think about momentum in the quantum case, we kind of think about it as mass as particles, or has that always been the case?
Say again?
Like, if you look at the classical correspondence to the quantum, momentum kind of loses its mass in some sense. Unless you're considering h, the Planck's constant, but I mean that's
Yeah.
just kind of like a distance. It's not really.
Yeah, you don't see the mass there, do you? That's
Well,
it.
I mean, like you can talk about an electron, but like in the
Right.
when you actually do calculations, we think about it as near massless, right?
Huh.
Yeah, well, these are like operators, so they're like expectation values in a way, right?
Oh, fair enough. So yeah, I guess the mass of the state is wrapped up in the eigenfunction for that particle or whatever. Yeah. Okay. Kinetic energy, of course, p squared over 2m. But over here, you got t hat, which is p hat squared over 2m. Your Hamiltonian, you know. So here, you know, excuse me. So now he's starting to use x hat as a vector. Look at that. So now he's really using xp, these as, you know, vectors, which is fine. Well, maybe he's not. I don't know. But certainly you could think about those as vectors, and then the Hamiltonian, you know, like minus h bar squared over 2m rats. Nabla squared plus v hat of x hat. All right, enough of this writing. I'm sorry, I'm wasting our time writing these things down at the moment, actually. Sorry, Adric. Can you see that?
Yeah, whatever. The white balance corrects, there it is.
Okay. All right. Correspondence principle, postulate 3. A quantum observable operator corresponding to a dynamical variable is obtained by replacing the canonical variable in classical mechanics by the corresponding quantum mechanical operator. All right, so this postulate gives a method to formulate quantum mechanical operators from the classical dynamical variables, which are made of canonical conjugate variables, P and Q. This goes back to Niels Bohr. All right. So he's trying to give us some kind of general breakdown of how this goes. He admits that there are things in quantum mechanics like spin and isospin, which have no classical analog. Postulate. So roughly speaking, this is postulate 3, right? I mean, it generalized a bit, but that's postulate 3, that there's this correspondence. Postulate 4, which I have not written all the postulates on the board, right? I've been trying to read them rather than write them. But postulate 4 is quantization. All right, quantization. And it says that every pair of canonically conjugate observables, excuse me, every pair of canonically conjugate observable operators satisfies the following Heisenberg commutation relations. So particularly Q hat M, Q hat N is equal to 0, which is P hat M, P hat N. And on the other hand, Q hat M with P hat N is I H bar Kronecker delta Mn. All right. So the example 1 that I did today was an example of that, because position and momentum are canonically conjugate variables, and these are the corresponding quantum operators to those canonically conjugate variables. Canonically conjugate variables, I think, is just referring us back to the discussion of like Lagrangian mechanics, where we have generalized coordinates and then their generalized momentum. So the pairing of like the Q's and the P's, where the momentums are defined by like partial derivative of the Lagrangian with respect to the velocity of the generalized coordinate. These would be, conjugate, I think. All right. So he throws some more equations at us here. Like he's got the commutation relations of angular momentum, which are, those are interesting, but I'm not sure what that has to do with the current discussion. But anyway, there they are. Yeah. All right. Okay, so let me read his jibber jabber here. It is now necessary to establish some sort of mathematical relationship between the state vector and observable operator, the quantum system. This mathematical relationship is formulated through the concept of measurement. Quantum theory of measurement thus forms a keystone of the mathematical structure of quantum mechanics. According to postulate 2, the only real values that can ever be predicted for an observable are the eigenvalues of the corresponding operator of the given physical system. As to which one of these eigenvalues will be obtained in a given situation, the answer to this question is expected to be determined from the particular form of the state vector of the physical system at the time of measurement. But the operations of the measurement generally affect the system, therefore it's almost impossible to predict a single measurement with absolute certainty. Naturally, this difficulty can somehow be resolved by dealing with large number of measurements under identical conditions, and then introducing the average of all results obtained. This average is called the expectation value of an observable operator, and it's defined as follows. So let's do that. I'm going to do it over here. Definition. The expectation. You're gonna have to follow real closely here, notation-wise, because he introduces a few different things that he's got a lot loaded into the notation. Starting with this, the expectation value. So he uses bracket. I mean, we're using bracket for so many different things. It gets kind of, okay, but this is the expectation value of an observable operator, which kind of begs the question, are there unobservable operators? I don't know. An observable operator, A hat, in the state. In the state psi of x of a physical system, all right, defined by A hat is equal to, so we do psi with A acting on psi divided by psi psi. So of course, if we're talking about a normalized wave vector, then the psi psi on the bottom is just 1, right?
Okay, yeah, that's what I was about to ask.
But he's not presupposing that. So he's kind of working our way towards that idea. We're not quite there yet. Let me get you over here a little bit more. And then, all right, another definition. Root mean square, I'll call it the RMS deviation. And he denoted by, and this is a little sneaky, he uses parentheses, nabla A hat, close parentheses. And it is the expectation value of A hat minus the expectation value of A hat squared in the state psi in which the expectation value is computed. Okay. Why didn't he just call it the standard deviation? Yeah, I don't know. It's the root mean square deviation. All right, root mean square deviation. Now, you're right. I mean, like, you're looking at how far the values of the operator are, like, away from the average value in some sense, right? Like, I said average, but I should say expectation value. Fine. What's a formula here?
He gives del A hat squared equals the expectation of A hat squared minus the expectation of A squared.
So it's the expectation of A hat minus, golly, what a horrible thing to write. This squared. I mean, he says it's, no?
Well, it's squared, and del A hat squared equals that.
Yeah, but this is, I mean, that's just.
Yeah, well, we got del A hat squared is that because the
Del A hat squared?
that's what it says.
Oh, the square root. It is the, I just jumped right over these two words, man. Look at this. I just jumped over it. Right here, square root. That matters. I just didn't even write it down. I didn't see it. So you're right. So this, if I can either put a square root over this or I'll put a square over here because that's less annoying. I'm just centering things here. It's all good. All right. And then how's that work out? Well, oof. All right. Man. Oof. So he's now assuming the state is normalized, I guess. Because he's not dividing by, you know, like, I mean, as far as I can tell, he's just assuming that this piece is gone because he's just doing that piece, right? I mean, so apparently psi is normalized now. I mean, I'm guessing. So a hat minus this squared acting on psi, and then how does he calculate that? How does he get the, how does he get, how does this come over here? Why is that true? So he passes this over to here.
Are you talking about the side, like how we pass from the square to like distributing the?
Right, yeah.
Yeah, I was thinking about that too. Oh.
What do we know about A? It's an observable, right? So what's that mean?
Oh, it's Hermitian.
It's
Yeah, it says that because A is Hermitian, and so, well, it's just like self-joint.
yeah, A is Hermitian, right?
Okay. Yeah, and that makes sense.
So then that means that like A, so golly, that means we have like A psi, good grief, A psi is psi, A Hermitian conjugate psi, right? But it's Hermitian, so that's A psi again. So we can pass A from one to the other. And then the same is true for the expectation value. I mean, this is,
It's just a constant, the scalar.
we can pass scale. You can always pass scalars, right, through the inner product. Remember, Roderick? Like if we got a 3 in the second input to the inner product, you can move it to the other one without constant.
But actually it's real. Right?
Right, but the expectation value of A is real because it's Hermitian.
Yeah.
So.
Oh, right.
So now once you've got that, and remember squaring of an operator is composition of the operator. That's what that means here, so that's logical. And then of course you've got, well, what do you have? You have this is just literally the length of the state A hat minus the expectation value of A acting on psi squared. And that gives us theorem 7.33, which I will write. Excuse me. Here it is, theorem 7.3.3.
Yeah, these are normalized. He uses them in the proof of this theorem, but he just uses the normalization as the proof.
Oh, okay. So the root mean squared squared. So the root mean squared squared is equal to the expectation value of the square minus the square of the expectation, and B, the expectation of the square of the operator is equal to the length of A hat acting on psi squared. Any?
So wait, he didn't say why we can just assume that it's all normalized, or he's just supposing?
Well, and I mean, I don't think.
I remember the same thing when I was taking quantum, that like you could just say this as well. Like it's particular cases like normalized.
Well, you know, I'm a little apprehensive about it because, like, there's a square root.
I don't remember exactly why, but it's not normalized. And
I don't.
Probably because we're taking, we're normalizing it so that we can take the statistical interpretations and get probabilities.
Yeah,
You're right. That's right. You can't do it if it's not normalized. You're right.
I think it has to be normalized because, like, I don't believe all of these formulas are true if it's not normalized. Like,
I think what Jacob's saying is on the nail. Is that
yeah.
You can't get realistic expectation values for these things if they're not normalized.
Right.
Or it wouldn't make sense. Or like answers just don't make sense if you try it.
Yeah. So this may be just a kind of editorial oversight of this chapter, in the sense that he is soon making the argument things need to be normalized, and I don't know, like. I feel like this is a failure of the editor of this book right here. That's what we're currently experiencing.
That makes sense. When I took quantum, it was like, okay, we gotta normalize this so we can take an expectation value.
Right. So we'll look at the proof here right quick. Since there's,
Did you move to?
I will move you.
Okay, if you didn't, I can look at the proof.
When I move, you move. Let's see here. There we go. All right, so I'm just going to jump straight to like the second line, which is fairly obvious. So psi with a hat minus the expectation value of a squared on psi, which is equal to psi with a hat squared minus 2a hat times expectation value of a. I'm really, really wanting to write a bar instead of expectation value of a at this point, guys. You know what I mean? Like, that would be, but it's too late. I'm too far in. But goodness gracious, if I was testing this, I would really, really want to have a different notation for the expectation value. It's so much writing for that. Good grief. Anyway, and more troublesome still, it looks so much like the other thing. Squared, of course, yeah. And then what? Then he just breaks it, uses the linearity, right? You got yourself a psi with a hat squared psi minus 2 psi with a hat psi, and then he pulled out, and here he can pull it out because this is real, so we can pull out the expectation value using Hermitian here. And then okay, and then since apparently we're assuming normalization, right? And he, in fairness, he may have said we're going to normalize psi earlier, and like last class we might have even said that, and then I've just forgotten, right? So maybe there's nothing wrong with the editor. The problem is just with me. Seems reasonable. And so that is the expectation of a hat squared, right? This is minus 2 times the expectation of a hat squared, and then plus the expectation of a hat squared, which of course gives us the formula for the variation. No, what is this? I feel like this is is this variation? I don't know. I forget. I'm bad at statistics, guys.
Yeah, it is variation. You can take the square root. That's deviation. Yeah, sorry. Yeah, it is that.
So yeah. And then part B. So that's part A. And then for part B, if we look at the expectation of a squared, we get psi a hat squared psi, which of course is a hat psi, which is the length of a hat psi squared. Okay, great, yeah. All right, so theorem 7.3.4, move along here. A necessary and sufficient condition for a physical system to be in an eigenstate of an observable A hat is that what's the name of this stupid thing? The root mean square deviation is 0, right? So I could say it this way. Psi is eigenstate of A hat, right? If and only if nabla A hat equal to 0. All right, so forward direction. Suppose, A hat psi is equal to lambda psi, right? Then okay, so then to calculate that, we need to do what? I mean, we've got this wonderful formula here, right? So we really just need to calculate the eigenvalue for A and the eigenvalue for the square of A, right? That's it. So like, so the expectation value of A hat is equal to what? It is equal to psi acting on A hat psi, which is psi lambda psi, which is lambda psi psi. Which he says is equal to lambda because he's normalizing his wave functions. Very good. Now I know that is, and again we're using the Hermitian. This presupposes A is Hermitian. And A hat squared is A hat psi, right? Which applying twice gives us lambda squared, right? Which works out to lambda squared. But then, if we look at the root mean square, we get lambda squared minus lambda squared, also known as a 0. So I'm using this formula and those calculations. So that is why if it's an eigenvalue, it implies the standard deviation, the root mean square is 0. Root mean square deviation 0. On the flip side, if, conversely, right? If you have the root mean square deviation 0, then how do we go and reverse this argument here? He does like this. He's like 0 is the square of this thing, right? Okay. Which by part B of the theorem is well, Obviously. Well, I guess that is fine, yeah.
Yeah, I think you're right. You keep theorem,
It is part B? Okay. So A hat minus expectation of A hat psi squared well, I mean, that means the, you know, we had that calculation somewhere up here before, I feel like.
I don't.
No?
Yeah, it's usually part A and part B.
Part A and part B?
Yeah, in part A, you set del A hat squared equals to 0. You get the.
No, well,
Wait a minute.
he's saying that the square of the. He's saying the square of the gradient of that thing is. What we showed is that the square of the the operator squared.
Yeah, it's norm squared.
Is the norm.
I see.
Is the norm squared. We did not show that.
All right. There is doubt. There is doubt. Give me a second here. So, yeah, you're saying? So this implies that the this thing, right, is equal to this thing.
Yeah. Yes.
And this is what?
And that's the norm of A hat psi.
Yeah, if that's the case, then you get the norm psi. But we know, but psi is 1. No, never mind. No, psi is not 1.
Yeah.
Don't listen to me.
But yeah, I see what you're saying. It's not the same.
Ah, curses. That's not even it. It's not that. It's not that.
Well, what you could say is that the square of the gradient of the operator, or the gradient operator.
That's the root mean square.
Wait a minute.
The standard deviation square.
This is literally,
is,
yeah. Yes, that's right. Yeah, by the definition of. This is, yeah, okay.
The standard deviation squared would give you the operator squared minus the it would give you the operator squared's expectation value minus the expectation value squared, or the expectation. So like you can get to from there to there. I think you should write that first.
Right, what first?
Just part A. This theorem, the theorem 7.33a.
Oh, that this is equal to the this.
Yeah. And then you get from the first term, you get that's equal to a to operator psi squared. Operator psi squared. No, that should be minus the expectation value squared.
Well, yeah, I'm not done. I mean, fine, minus the expectation value of A.
Yeah.
Squared, okay.
And this has to be the line, I think. It's not. I don't think it's an equality, but you totally have a triangle inequality somewhere.
I think.
So the I think it's just I think it's just the definition of.
Yeah, it comes from the definition of the root mean square and the expectation value.
I think it's I think we just have to go back to where we started. It's annoying, but it's literally just the definition of the root mean square that we're getting stuck on.
And then so.
So
Self-resolving for me, so it brings you over, so that is the norm of that square. Yeah.
So we have A hat minus the expectation value of a hat acting on psi squared. I mean, this is literally equal to that because that is the that is what we had back over here. Well, I'm sorry, I have to give me a second here. See, that was our definition of the root mean square, and then going back over to here, then what?
You drop the norm.
Right. So if the
0.
okay, so the only way this can be 0, it's a norm, right? So that means that a hat minus the norm of a hat minus the expectation value of a hat. I hate these terms. Is equal to 0. But that's the stupid eigenvalue equation, right? Yeah, ergo a hat psi is equal to constant expectation value of a hat times psi, which says that that's an eigenvalue. That's the lambda. And of course the psi is non-zero, is assumed because, well, we're working with psi normalized, so apparently it's non-zero, right? All right, enough of this. Goodness gracious. Sorry, guys. I've eaten a stupid amount of our time on this rather silly point. All right, so what's this come to next here? Well, he says thus, excuse me, if psi n of x is an eigenvector of A with corresponding eigenvalue lambda n such that the eigenvalue equation holds for all n, the expectation value in the orthonormal eigenstate is given by, oh yeah, let's write that down. All right, you write that down. Where was I? So we're assuming a hat on psi n is lambda n psi n, so that's how we're labeling our eigenvalues, right? And this is an orthonormal basis of eigenstates for A, right? Then the expectation value of a hat is equal to psi n a hat psi n divided by, so we're all right, fine. They're not normalized apparently now. I guess they are normalized. My bad. Okay. I guess that's the thing, is if it's equal to 1, you can still write it, right? Fair.
Well, I guess it doesn't matter, because when you convert to the lambda n is real, so you just pull it out.
Oh. Yeah, you're right. So that's interesting. This calculation survives whether or not psi n is normalized, doesn't it? Interesting. He says, on the other hand, if psi of x is not an eigenvector of a hat, it can be expanded into a complete orthonormal set of eigenvectors. Consequently, let me just say this generally. Psi of x is equal to the sum n equals 1 to infinity of Cn psi n of x, right? Which you could, of course, calculate the coefficients using the usual inner product shenanigans, namely psi n with psi is the coefficient that is the Cn, right? And more than that, the length of the wave, the length of this the length of psi of x, right? Which I suppose I should probably call it a state vector, right? The length of the state vector is what? Yeah, right, Parsifals, yeah, I guess that's true. So it is just the sum n equals 1 to infinity of like the modulus of Cn squared.
In that case, it would
Um, right, and well, I don't know if it is an orthonormal set. Is it normalized? Well, psi doesn't have to.
Oh, it's orthonormal.
I guess psi is not. Psi of x isn't normalized just yet, but the psi,
Yeah, no, I was talking about the size.
the psi sub n's are normalized.
Yeah, sorry.
No, you're fine. I think we're trying to bridge the gap between the normalization of the psi's versus the normalization of psi versus normalization of the eigen, the psi sub n's. All right, and then he's got this, this beautiful multi-step calculation, which I will go through. Oh man. Oh, yowzers. Here we go. So the expectation value of A is equal to 1 over the normalization of psi squared times bracket of the sum m equals 1 to infinity of c sub m psi sub m against A. Hey, what happened to the hat? It's got no hat there. He's been pretty litigious about the hats. All of a sudden, no hat. Let's see here. See, and don't read anything into that. It doesn't mean anything. It's just a typo. Like that. And then, of course, what happens is this comes through here, hits that, and just gives you, you know, very tempting to just erase and write over, but I will behave. So what we got is a Cn lambda n psi n, right? And then we can pull out the sum over m, the sum over n, and we got a Cm, but we pull out a C conjugate n because we're pulling it out of the second slot, right? And then what we got left is the psi m bracket psi n, which this is an orthonormal eigenbasis, right? So that is straight up. And I forgot, I've lost my lambda bar n technically. Yep. Right. Of course, the lambda need not be complex, right? Because in fact, this is a Hermitian operator. So, and as you're just telling me, Audric, this is in fact Kronecker delta mn, which is the natural enemy of one of these sums. So what you got is you got 1 over the length of the state vectors squared. We'll keep the n. Sum n equals 1 to infinity of Cn conjugate. Lambda was real, we know it, like that. Right, so apparently that is equal to whoa, what just happened? Whoa.
What's going on?
I'm just processing the next step here.
Okay.
I'm processing. Okay. Let me write it on top of the board. Top of the board to you.
Oh, you wrote it. You wrote it.
All right. So we got.
And then
Yeah, we
just
mm-hmm.
divide by the whole thing.
Oh, we have Kronecker delta. Yeah.
Take this. Oh, you're wondering where the norm squared turns into.
I'm just processing. Yeah.
Or Cn.
Well, it's the.
That's what we had above. Yeah, we already had that in the beginning.
So we got the.
Okay.
Got it. Yeah,
You're right. Yeah.
I was wondering.
So
then you can pull out the entire sum.
the norm psi squared was the sum of,
And then you just define it.
I'm going to use a different index here, m equals 1 to infinity. I mean, it's not the same m. I shouldn't use n for both.
Yeah, they have it as the same.
Yeah, you really shouldn't.
Okay.
I don't think. Because they're different sums. And, you know,
Yeah, but they're both of Cn.
well, sure, but, well, no, actually, this one's of CM.
Well, they changed it in the book somewhere.
Do they? They might.
But yeah, like from the bottom of the board to the top of the.
Yeah, he's got n for the top and the bottom. So he,
You think that's a typo, or do you think?
I don't know.
No, it has to be because the sine squared gives you a Cn. It gives you a sum in Cn, so they have to be the same index.
Well, you can write this formula with whatever letter you want. My point is you shouldn't use the same letter that you've already used because it's a different summation. But it's okay.
So he pulls the top one out then.
Yeah, and so then what's going on here is this is an infinite sum, right? And so you can rewrite that as the sum n equals 1 to infinity of, you know, Cn squared lambda n divided by this number. That's not lambda, that's lambda sub n.
And then you define the Cn over the sum as a an.
Oh, is that what he does?
Oh, just,
I was wondering where that an, I was like, where's this stupid an come from?
He just
Oh.
defines it.
Okay, so a sub n, lambda n equals 1 to infinity, where
Don't you have to show that an's convergent though?
where lambda n is equal to the sum m equals 1 to infinity.
Or do we have a property
Oh, my bad.
that we can abuse?
Where lambda n is the sum, the absolute value of Cn squared divided by the sum m equals 1 to infinity of the Cm squared. All right, like that.
Do you not have to show that's convergent? To get the an? No, not you wrote lambda n by the way, but
That is, I'm telling you, this is really annoying to me that he's writing the n in the denominator there. Like, I object. I object.
wait, so I might just be asking a ridiculous question, but do you not have to show an should converge to get an like that?
Well,
We know that's going to converge because it's equal to the norm squared.
convergence of,
Because
well, we know, we're assuming it's a complete orthonormal set, so the convergence of the coefficients, I think, is,
it's the norm of psi squared.
yeah.
So does that just show convergence then?
Yeah,
Well, if the norm is theoretically infinite, then, you know, it'll converge because you just have a finite term.
So this is,
Oh, wait, no, never mind.
this we can rewrite as what? It's the, so it's the modulus of the bracket of psi n with psi squared well, this isn't lambda, this is a sub n, not lambda n, dummy. Me, not you guys. A sub n is equal to that, which is also equal to this. And I just, yeah, you know, no, this is the sum. And I insist on using a different letter. I'm sorry, m equals 1 to infinity of the absolute value of psi m with psi squared. And the reason I insist on using a different letter is n is free. It's a free variable in this equation. It has a specific meaning, and that meaning is attached to this right here, but it is not attached to this down here. That's a sum. That's over all n. That's m equals 1 to infinity, right? It's not fine. All right, anyway, so what's the story here? Result 7.76, which is this one. It's interpreted as the outcome of a large number of measurements under identical conditions. In other words, the expectation value of A is the weighted average of a large number of measurements of the system. According to postulate 2, each measurement yields one of the eigenvalues of A hat belonging to the set lambda n. Oh, here enter lowercase a hat. Keep in mind, this is also a typo that is in uppercase a hat. At no point have we defined lowercase a hat. I strike lowercase a hat from the record on page 375. Just saying. Just notice that.
What are you you're saying, in other words, the expectation value they have?
Under equation 7.7 hat, like the fourth line down, it says each measurement yields one of the eigenvalues of lowercase a hat belonging to the set lambda n. No. That is a uppercase a. Okay, so equation 7.77, which is this one, this guy right here. All right, equation 7.77 represents the frequency with which the eigenvalues lambda n occur in the measurement. And while the denominator of 7.77 is the total number of measurements, hence the ratio of the frequency psi n with psi squared to the total number of measurements, sum over n equals 1 to infinity, psi, this is going to be m equals 1 to infinity, psi m with psi squared, represents the weight a sub n of the eigenvalues in the measurement. He says this clearly leads to a statistical interpretation of a sub n as the probability, let me write that down. A sub n is the probability that a measurement will yield eigenvalue lambda n for operator a hat prepared in state psi of x of the physical system. Furthermore, it follows from 7.77 that the total probability, sum n equals 1 to infinity of a sub n equals to 1. And this reconfirms the statistical interpretation, since a sub n is the probability that a single measurement yields an eigenvalue of a hat. So yeah, if we take the sum n equals 1 to infinity of this, then we get sum over n versus sum over m equals 1, right? Cool. All right. Now, what if psi is the normalized wave vector? Then what do we get? Let's see here. So if for normalized state, ow! Yeah, I'm okay. I'm just, every pinch your finger harder than you should.